Hi guys, welcome back to the channel. So I have decided to create a playlist on computer science fundamentals. So in this playlist, I would like to explore some core concepts of computer science to understand how they actually help us to build some enterprise level applications. So I do understand that in our channel I did have a lot of videos explaining about how the code works and how the SQL queries and other things work. But I felt that it was very abstract and it needed some more understanding of a certain concepts to be able to understand its real working and its real world use cases. So for the same, I wanted to start this playlist. So in this playlist, so first I'm going to start with the DBMS, and then we'll go into the core concepts of the DBMS. Like we're going to explore how SQL works internally, and then how transactions work, and we will see levels of queries, and then we'll conclude with some advanced DBMS topics like how stored procedures work and others. So in this video, let's start with what DBMS is. So, even before starting with what DBMS is, let's break down the term uh, DBMS. So, DBMS actually stands for a database management system. So, if we try to break down what DBMS is, so the DB itself stands for a database, and a management system is a software which is running on the top of it to manage certain things. So we'll see what those certain things were. So what is a database? And so even before defining a database, let's try and understand what a data is. So in real world, any information, anything, anything which can be quantified, anything which can be measured, anything which can be observed, can be called as a data. So in terms of computer science, we say anything that is put uh, any information or any fact can be a data. So how do we handle data? And also we are also hearing these terms like data is the new currency. So using data, there are many tech giants like Google and Facebook. They all depend on data. So it is inevitable that if something is is a very important in a certain field, you need certain algorithms, you need certain functionalities, you need certain operations to be done on that particular thing. In a similar way, the data, it can be of anything, it can be anything, it needs to be processed. So how the data is processed and stored? If we get into this discussion, so we can see two types of memories. So I have one thing called as memory and another thing called as storage. So from a memory overview, it might seem that both of them they actually do the same thing, but it's quite different how a process works in a computer. So memory is primarily we can think of RAM. So RAM is a, a volatile memory, and it is one of the primary memory. And then for the storage, we can think of hard disk, we can think of SSDs, floppy disk, any external device that is capable of storing data, yeah, which is capable of storing as well as capable of retrieving the data. So we can classify it in a way. So how data is processed? So data is processed in the memory, and data is stored in a storage area. So which one of them is important? So we cannot say that because both of them are equally important. But what actually stands out is the storage, because whatever the process, so whatever the processing that we have done will only exist for a certain amount of time. But if we want that changes to be persistent, we need to save that updated information. We need to save the processed information into a place. So that's what we call as storage, right? So a hard disk. So in comparison, we can say that memory is relatively faster because of the technology used. So in memory, we use the DRAM technology, usually the dynamic RAM, which is made of uh, capacitors and transistors of a certain type. So they work faster. But for storage, we usually go for magnetic disks and other things. So they're relatively slower because of their mechanical features, and memory is faster because of its electronic support. So given that, so we do need memory as well as storage, but how the data is processed and stored. So they will be stored in the memory and storage, but what governs all these things? So it is we need a system that makes sure that everything is properly placed, everything is properly retrieved. So even before the storage of data was an issue, we we had file systems. So what did file systems offer? So file systems, they usually have a file allocation table, which we normally call as a fat table. So it will have the information about the location at which the blocks of file was placed in the memory, and using that we can just go out there and retrieve all the blocks of file. So this was a very efficient a system, and in most of the early applications, this was supposed to be enough for any use case. Yeah, but later when in the late 1970s, where people have realized that uh, the the computer system is not just only for processing some raw information. So they wanted to bring in the real world entities, they wanted to bring in real world businesses into the computing system, and let some some complex computations and some hectic works to be done to be automated rather than being done manually. So when this idea came out, object orientation was another thing which has also flourished for the same reason. So in this way, so people have understood that, so we needed some other system which can offer some additional functionality than just storing and retrieving the data. So we came up with something called as DBMS. So, but what is DBMS, and how does it fulfill the actual purpose of manipulating data in a very efficient way? So let's talk about the uh, a DBMS versus file system. So the very important aspect that actually makes a big difference between both of them is the ability to know the data. A, f- a file system will only handle the data in mostly a text format, um, or maybe technically we can say in the a UTF-8 format. Yeah, but it doesn't have any control over what kind of data is being written into a file, and what the file contains, and how should it be interpreted. I mean, it's not, so it is not of its concern. So a file system will only manage the storage of it, only manages the storage of data into blocks in the memory, and a retrieval of the blocks using some kind of a directory information. So this was very efficient and a very low level a use case of any a storage system. Yeah, but what DBMS offers? So what was lacking in file system? It was the same thing. We don't have anything that is governing the kind of data that is being put in a file, and also we don't have any mechanism that allows us to manipulate multiple files at once. So there is no concurrency, there is no control over the data, and there is no ability to extend functionalities, like to extract a certain amount of data, to extract a particular amount of data, to filter the data, to manipulate the data, to insert dynamically, to do a lot of things. So file system never had as such support. So we went for the we went for a DBMS. So how DBMS works? So we can see in this picture we have a database. A database is nothing but the hard disk that we have seen. But then if a database itself is hard disk, then why are we calling it as a database? I mean, we could just call it as a storage device, right? No, a database will have a slightly different meaning. So a database is a collection of a data as 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 in storage, but the data can be described as a related data for a particular business purpose. So whatever the data that we have in a database will have a purpose. It's not like that we have some random files, we have some random txt files, some images, and some videos and some excel files. We just place it in the database. So no, it will not allow it. We can only store the data which is related, which is meaningful, and which has a business use case, which has some which has to be in a certain way for a certain business to run. So there will be some kind of restrictions, so there will be some kind of implementations, and there will be some kind of constraints applied on the data. And all this related data is not going to be stored in a very easy way. So we will use some sort of sophisticated algorithms like the Beatrice and maybe some other and also some other indexing techniques. So there is a lot happening in the storage area. So it's not just a normal storage device. So we call it a database because we know that we are placing all of a certain entities things into a place. So everything within a single database can be considered as all the data which is required for a certain business. So that's how we can define a database. Now, who can interact with the database? So we have a developer here. A developer could be an application developer. So he might be needing some kind of data from the database. And a user could be a naive user. So a naive users will have a GUI to interact to actually kind of request some data to view some data. So they will have some kind of a GUI, and using that they will pass on some sort of commands, and it has to be received, and they have to be returned in a specific way. And then we have application. So applications can request using APIs, using uh, some sort of a function calling. So all these end users, so they need to use the database. But if they were to use the database, so as we have discussed, we don't store it in an ordinary way, and it's not very straightforward. We use some kind of relationships. So there is no way that a developer or a end user or an application can interact with the database directly. So it needs an interface which abstracts all of these things. So we needed some system, and we called it, so since we have a database and we needed a management system, we called this software as DBMS. So this software called DBMS provides some APIs to all the developers, users, and applications. See, the API could be anything. For developer, it could be the workbench or any kind of command line interpreter, and for the user, it could be a GUI application, and for application, it could be an API. So using all these technologies, it is going to allow the end users to easily interact with the database. And after receiving some request, when it receives any request, it is going to capture what is needed, and it is going to plan what is needed to be extracted, and then it will go to the database. It will have all the algorithms to retrieve the data, and then after retrieving it will it is going to present it to the users. So this is how DBMS abstracts all this complexity and makes the usage of DBMS almost as easy as a file system. So that's a big breakthrough, right? So this is how DBMS makes it easier for us, right? So moving on, we have the types of DBMS. So the DBMS in originally were only supposed to be relational, because in the early days we went for object orientation of things. So to create anything which existed in the real world, we went for creating an object in a programming language and creating entities in a database. So that's how the mapping was done. So relational database was one of the most foundational ways in which the data was stored, and it's often regarded as the most efficient way of storing data in rows and columns in a form of matrix, literally. So it was called relational because these are not just a matrix like tables. They had some meaning, and also they had relationships with other tables. It's not like uh, one table is independent of others. No, they're all related. So that's why we call them a relation, right? And then we had something called as analytical OLAPs, OLAP systems, online analytical processing. So this is more of a relational thing. So and, I, and actually I forgot that there is something called SQL. So we will go deep into what SQL is in our upcoming videos. But uh, to give a fair idea, so SQL is a certain way through which we can ask the DBMS software to retrieve some kind of data for us. So SQL is kind of a language, so that will help us to write commands. So yeah, and we will get back to it. So coming back to OLAP, online analytical processing systems. So these systems, so they do processing. So they do the analytical processing on historical data. So the relational, so whatever the data that we are storing over the years, over the last few years. So when we need to analyze what's happening and what are the trends for the and to understand any kind of trends, to get any kind of insights about the data, so we can use this OLAP systems. So they will give you a lot of uh, so so they do have some kind of algorithms. So they do have some data mining algorithms to to kind of fetch all these things. So it's more on the analytical side of things. So we're not very much into them. And and then we have something called as a NoSQL databases. So NoSQL databases came after the relational databases. So relational databases did had some kind of issues because they're not so much flexible. So in this modern era, we needed some other, some newer technology to kind of hold the unstructured data. So we went for these NoSQL databases. So one of the most important one was this key valued thing. Yeah, because one of the most used in-memory database is called Redis. So Redis is going to be used in enterprises of a way lot than anyone can expect. So it uses this key valued technique. And then we have column family. This is somewhat similar, but it allows us to expand the columns. So it's kind of, and then we have graph. So this is more of inspired from a network databases. So we will have all these entities connected as graphs, and and there is actually a special language called GraphQL for this. So using GraphQL, we can query on a graph. So I don't think it's needed at this point of time. And the last one that we missed is the document based. So one of the most famous document based DBM software is a MongoDB. So MongoDB is a NoSQL document based database. So these are mostly the a classification of the database systems, right? So now let's move on to who needs the databases and who uses them. So we did discuss that a databases are needed for the businesses, but who uses them? I mean, who can create them? Who can manipulate them? Who has access over the data. So we have four actors on this end. So one is the database administrator. A database administrator is actually the most uh, powerful person who in terms of a database is concerned. So he'll be administering all the uh, database requirements, all these the ETL pipelines. Everything is going to be managed by the database administrator, and he is responsible for maintaining the database. And then we have a database designer. So a database designer is more concerned with how the tables and entities are to be constructed. So that is more on the designing side of it. So we use something called as ER diagrams and UMLs to kind of define how the data is supposed to be stored in the database. And then we have end users. End users are just the casual users and naive users. So they're not very particularly expertised in handling a database. They only want to view whatever the data that is present. So we are going to provide some kind of interface for them to work with, which is easier for them without being explicitly able to alter the database. So, and we have system analyst and application programmers. So application programmers is what normally we do as a developer. So as a developer, we do interact with the database, but not in a very direct way. We use our programming APIs to make some kind of a procedure, to make the procedure calls and ask the database to do certain things for us, and we can invoke some functionalities. We can implement, test, debug, and document a lot of things. So these are the four actors who work on the database. So all of them have different purposes, and all of them have a different level of access on the database as well, as the a database administrator having the highest amount of privilege on the database. And moving on, so this is the view. So how end users see the database. So we have three users. Each of them has their own view. So any database would normally be of a very large amount. I mean, you cannot often give the entire copy of a database to any user. So first you have to understand the user's requirement and only fetch those data which has to be presented to them. So in that way, we need the view layer. So the view layer is only concerned with the presentation of the data as a table to the end user. And then we have something called as the conceptual schema. Let me erase this. So we have this conceptual schema. So this is the most important part that we need to understand, because the conceptual schema is where we define the relations, where we define the references, where we define views, we would define a lot of things that makes the database efficient. So we do the joining, and everything happens at the conceptual level. The conceptual level is where the database designing, administration, everything has to be everything works, right? And then we have the physical schema. So physical schema just is about how do we store it in the database. So here we are concerned with how we use indexing, how we use B trees, B plus trees, the blocks, a segmentation, and all these things, they makes. So they are used in this physical schema to make sure that so when we are storing them in the database, we'll be able to retrieve it efficiently, and when we need to update it, we can update it quickly. When we need to insert it, we can insert it quickly. So we'll ensure that everything of them will be possible, right? So this is how the interaction happens. And then we'll coming to the database interaction. So we have seen that, so database is offering a lot of functionality, so it's a very powerful system. Then if it is a very powerful system, then we need some way to access all of its functionality. Then okay, so we need some way through which we can say, you know I need these things, and I need certain things in a way. So how do we provide all this information to a database? So usually in the programming, we write programs. The programs will be compiled, and some kind of a bytecode will be generated, and using that bytecode we can ask the CPU to run all them, and to perform all the computation and return some result to us. So in a very similar way, for this database, we can give something. So for this DB, we can give something called as a query. So what is a query? So we will get uh, deep into what a query is and how it looks and how to write multiple types of queries. So a query is just like a question. I'm asking the database, okay, give me this table. Okay, so the way we write it is going to be defined. So we will talk about it later. So using something called as a query, we are going to ask the we are going to ask the a database to do certain things, and interpreting what we have asked, the database is going to process it, and after processing, when it is ready with the result, it is going to present it back to us in the form of table, of course. So a query is the way we interact with the database. Is it the only way? It's mostly the only way for application programmers. A database administrator might have some other ways or other APIs to work with, but using the query, an application programmer can request resources, can make manipulations on data. Anything on the relations can be done through a query. Now, how do we write a query? We will see how do we write a query, but now let's see how a query works, right? Okay, so this is the workflow of a query. So query in a high level language. So usually the query is very similar to English language. So it's a very high level thing. It's not very machine level. So a very so this high level language, it will be given to a parser and a translator. So it is going to interpret what is being asked. So let's for example say that we did a query to select a certain records. So the selection of the records is our query, and it is going to be translated into its intermediate form. So a different databases may use a different representations of the query. uh, Anyway, so when they are ready with the representations, so they will be going through a step called query optimizer. So query optimizer will have the a DBMS catalog. So what is a DBMS catalog? So DBMS catalog can be seen as a metadata, or it is a repository that will hold all the information about the tables, the relationships, entities, and their constraints, keys. Everything is going to be there in this catalog. And using all that information, this query optimizer will try to optimize the query that we have been. If we are asking for some sort of redundant data, it is going to optimize the query. And if we are asking for something that's not available, or if there is any mistake in our query, then it's going to throw us some errors, uh, as saying that the semantics are not matching. I mean, we cannot find the table that you're asking for. So all these checks are going to be done. And after this, a query optimizer is ready with a plan. So we call it as an execution plan. So this execution plan is just a set how the DBMS is going to fetch the data, how it is going to present the data. So we have this execution plan. So the execution plan is going to be given to the query evolution engine, as well as the instance of a database. And always remember, the database will always persist in the storage. Only the instance will be given to the user. So using the execution plan and the data, we are going to give it to the query evolution engine, and there we are going to get the result of the query. The result of the query will be further will be given to some output parsers. Output parsers are going to create a table-like interface such that we can view that in a better way. So this is the plan. Okay, now let's discuss what should a DBMS offer. So as we know, it's a DBMS is nothing but a software. So for software, we usually have some sort of requirements, right? So when we are designing a software, we expect the software to do some kind of things. We want it to provide some kind of functionalities. So what are the expected functionalities of a DBMS? Not any DBMS, a good DBMS. So what are them? So the first one is the data concurrency. So this was a major so this was one of the major issues in the file system, right? So file system cannot handle concurrency. It can only work with one file at a time, or maybe it can. So it's not so sophisticated that it can handle the data concurrency. But DBMS was designed to be concurrent. So what is this term called concurrency? So concurrency is nothing but the ability to run multiple tasks at a time, not sequentially, not it it could be in any order, but the ability of all of them to be present in the memory, to be processed in the memory at the same time, you know, in a different way of scheduling. We call it concurrency, right? And we will discuss more about the data concurrency in our transaction video. So as of now, just try to understand that. So this is how a schedule looks inside a database. So there will be multiple transactions running at the same time. So a transaction is nothing but any operation on the database, usually a read operation or a write operation, or maybe both at the same time. So this is what we call a transaction in a very light way, in a very light-hearted way. So multiple transactions are now running simultaneously, right? So this is what we call as a schedule. So the schedule describes how at what point of time what part of the transaction needs to be executed by the CPU. So using the scheduling, we are achieving the concurrency, right? Now let's go to the second one. It's called the data integrity. So a data integrity is the most important feature, or actually this is one of the feature that was the major reason for the existence of DBMS, the data integrity. So we can filter out, or we can enforce some rules on what sort of data that can be inserted. So how can we enforce rules? Yes, through SQL we can enforce rules, but what are those rules? So the classification of data integrity, we can see that we have physical integrity and logical integrity. The physical integrity is not in the control of any software because it is managed by the hardware. Of course, we do have some sort of algorithms like RAID and all these things, which make sure that the data, the multiple copies of data is present, such that a recovery management can be done. Yeah, but the physical integrity is not an issue of the database. Yeah, but the logical integrity can be managed by the database. So what is this logical integrity? We have four of them. So we do have four of them: entity integrity, referential integrity, and domain integrity, and user defined integrity. So entity integrity defines. So so okay, now let's. I think it would be better if we start off with the domain integrity, which is easier to understand. So domain integrity defines. So what kind of values can I insert into a specific column? So we discussed that every relationship has columns and tables, has the columns and rows. So the columns, so we can define what kind of values can be entered. So let's say, for example, we have some field called age. So we know that the value cannot be negative. So why do we? So I mean, why should we allow any a negative value to be inserted? So we can imp enforce the rule. We can impose that if any negative value is being entered, you just throw an exception. You just don't allow that, right? So in this way, we are maintaining a restriction on the domain from which the data can be inserted. And then we have the referential integrity. So referential integrity, uh, so we can achieve this using a foreign keys. So this actually ensures that a relationship, if it has any reference to another relationship, they so the both of these tables, uh, as one of them is a referring and one of them is the referred table, so they both are having some sort of integrity between them. And then we have the entity integrity. Entity integrity is managed using keys and some other mechanisms through which we ensure that whatever the data which is in the relation is very consistent and clean, and as well as a very uh, a, it will improve the data quality of our database. And the last one is the user defined integrity. So it is not known to the system that what your business is all about. So in such cases we want to define some set of rules which are very close to our business, so which are not defined in the database itself. So for such cases, we use a user-defined integrity checks. So we will see how they how to enforce them syntactically. And the last one is a no data redundancy. So what is this redundancy? In file system, it is often it's not often, but it is very much possible that a lot of data is duplicated in a lot of files, but the file system is not aware of the duplication, so it will just allow all the duplicate things to be inserted again into the database. So it makes a lot of red so a lot of space is being utilized for storing them uselessly, right? So the DBMS eliminates a such thing by ensuring that only the unique records, only the values that are needed, only the data that is not available others. I mean, which is a specific is will be only stored on the disk. So it can be achieved through a process called normalization. We have a lot of normal forms. Usually for any enterprise level application, we need to ensure that at least at least the normalization was done up till 3.5. So we'll see what are the variations of normalization, and this has to be given. And one thing that I kind of missed is, so while discussing about the data concurrency, usually in many of the databases, the default isolation level is called as a read committed. So what is read committed? We are going to discuss it in the a transactional a video, I guess. So that's it, and I think I have given a good overview of what a database management system is and why do we need it. I think we do understand that what the data is and what a database is and what a database management system is, right? So this is so I think I hope you understand this. So we'll meet you in another lecture.